Hi, we're going to be looking in depth at a PV diagram problem. This problem's a little bit more complicated than the ones we've done in the past. So I have 3 moles of an ideal gas taken along the cycle shown in the diagram. I want to determine the change in internal energy, the heat, and the work for each leg of the entire system. Okay, so we're going to be working with some equations here. The first equation we're going to work with, obviously, is going to be, shoot, I already messed that up, is going to be the work is negative P delta V. The change in internal energy is 3/2 nR delta T. We're going to work with PV equals nRT. And we're going to work with the fact that the change in internal energy is Q plus W, the heat plus the work. All righty. So now we can get started. I'm going to go ahead and look at the work first. The work is by far the easiest of the 3 things to calculate. And since we want each leg and we want the entire cycle, there we go, there's my cycle. So I want all of that. So we're going to go ahead and make a chart. I'm going to say this is leg AB, this is leg BC, this is leg CA, and this is ABCA, or the entire cycle. And I'm going to make a chart. So the work is negative P delta V. All righty. So from A to B, the change in volume is 0. That's an isochore. I can just write 0. That's cool. And from the B to C, I can say that that's negative P. Well, the pressure here is 1,000 pascals. By the way, I made up these numbers, so they might be a little cattywampus. We're not going to let that stop us. The change in volume, it's always final minus initial. So we're going to go 9 minus 3. Well, negative 1,000 times 9 minus 3 is 6. So we have negative 6,000 joules. That's not too shabby. From C to A, I didn't really give myself enough room here. I've got both the volume and the pressure changing here. The only thing I can tell you right now is that it's going to be positive. I can tell you it's going to be positive because it's negative on the lower leg. And so it's got to be positive on the upper leg because it's going in the opposite direction. This one is compressing. This one is expanding. So I can't figure that out. What I can figure out, however, is that the area of the cycle, or the work done by the cycle, is the area of the triangle. And I know that the work, let's smudge over here for just a minute, the work of each leg, as we did this in the previous lesson, the work from each leg is the total work of the cycle. So here's what we're going to do. We're going to get the area of that triangle, and we're going to get the work of that cycle. Once I have that, I know this one. I know BC. If I know the cycle, then I can use those others to determine the work done on this part of the cycle. So let's go ahead and do the area of the triangle. That's 1/2 the base, which is 9 minus 3. 9 minus 3. And the height, which is 4,000 minus 1,000. We'll look at the sign in just a minute as well. So that's 1/2 times 6 times 3,000. That's 3 times 3,000, which is 9,000 joules. That's a positive number. So let's decide, since this leg on the bottom is negative, that's expanding, this leg on the top going the opposite way with the compression of the volume's got to be positive. I'm moving in a counterclockwise direction, so that work is positive. So that's 9,000 joules. So I'm going to say then that the work from C to A is the total work, A, B, C, A, minus the work from A to B, minus the work from B to C. Well, A to B is 0, so woohoo! C to A, that's what we're looking for here. The total work is 9,000. And the work from B to C is negative 6,000 and the negative of a negative. So we wind up with the work from C to A is 15,000 joules. That was a lot of energy it took. And that makes sense because we're compressing it and we're increasing the pressure at the same time. So we're not just compressing it with constant pressure, we're compressing it and increasing the pressure. So it makes sense that that's going to have a significant amount of work done. And it also makes sense because that's a positive value. This number needs to be more positive than this is negative because I had positive total work done. If we were going the other direction, my work would be negative. Okay, so now that we have the work done, let's change to the internal energy. Change in internal energy, that's going to be 3/2 in 3/2, not 3/3, 3/2 in our delta T. Excuse me, which means I'm going to have to know the temperature at each vertex of this triangle. Okay, so we're going to have to do a little work here. So PV equals nRT. I know the pressure and the volume at each, and I know that the number of moles is 3, so that's N. And I know that R is 8.314 joules per mole Kelvin. And since I'm in SI units, pascals, and cubic meters, I made sure I did that because I wanted my life to be easy. This is going to get me my temperature in Kelvin. That's going to be PV over nR. Well, let's calculate N and R. So that's 3 times 8.314, which is going to give me 24.94. Okay, not worrying too much about sig figs here. So that's going to be the same in each of those calculations. So the temperature at vertex A is the pressure at A times the volume at A. So I'm going to go to A here. My pressure is 4,000. My volume is 3. My pressure is 4,000. My volume is 3 over 24.94. So the temperature of A, and that's going to be 12,000 divided by 24.94, and that gives me 481 Kelvin. That's reasonable. All right, so now let's do the temperature of B. Well, let's look at vertex B. My pressure is 1,000, my volume is 3. 1,000 times 3, and the N and the R are going to stay the same, so I'm just going to make that 24.94. And the temperature at B is now 3,000 divided by 24.94. And I get 120 Kelvin. And my temperature at C. Well, temperature at C, I've got 1,009, 1,000 pascals and 9 cubic meters over 24.94. And I get 361 Kelvin. Okay. So I've got a different temperature for each one. Now I can determine the change of internal energy from each of these because I have the change of temperature from each one. So from A to B, that's going to be the internal energy of B minus the internal energy at A, which is simply going to be 3/2 in R times TB minus TA. Yep, I know I made that too squishy, but that's okay. So 3/2 NR times TB minus TA. Well, the 3/2 NR is going to be the same for all of the pieces. So I'm going to go ahead over here on an aside and do 3/2 times 3 times 8.314. And that's 9 divided by 2 times 8.314. And I get 37.413. Alrighty. So I've just gone ahead and calculated that coefficient to make my life a little easier. So my delta U from A to B is 37.413 times TB, 120 minus TA, 481. Notice my internal energy has decreased. I'm going to have a negative change there. And so I wound up with negative 13,507 joules. Wow. That's nuts. Negative 13,507 joules. Okay. Whew. I told you guys this was going to be complicated. So this is now going to be UC minus UB, which is 3/2 NR, which we already have that coefficient, times TC minus TB. And this one's going to be positive. So from going A to B, our internal energy, we dropped the pressure with keeping the volume the same. Well, that stands to reason that we would lose internal energy because we're not hitting those sides as much, so the temperature would drop. Okay. And alrighty, so that's going to be 37. I'm going to do some arithmetic here. Times TC is 361 minus 120 times 37.413. And I get an internal energy of positive 9,017 joules. Yep, I am rounding like nobody's business here. So I got some of it back. Some of that temperature increased back. I increased the volume, keeping the pressure the same. That makes some sense. From C to A, see, we had to do something cattywampus over here. This, not so much. So from UA minus UC, Coolio, 3/2 NR times TC minus, or sorry, TA minus TC, 37.413 again. And A is 481 minus 361. Cool. So 481 minus 361, I get 120. And times 37.413. So that gives me 4490 joules as my delta U. Alrighty. You ready for some fun? The whole system. I started here. I want to go down. I come over. I go back. I'm at the same spot. So my delta U has to be 0. Has to be. There's no other option. I wound up at the same temperature. TA minus TA is 0. Let's verify. I might be a little off because I've been rounding. If I added all those up, negative 13,507 plus 9,017 plus 4,490. So negative 13,507 plus 9,017 plus 4,490. Lo and behold, I got 0. I absolutely got 0 there. So we basically have just proved that all of these changes in internal energy complete the cycle. Those were the hard parts. That was really hard. Now, we always take heat to be the hardest thing to do simply because it's not intuitive. It's the energy that's transferred. So we think it's the temperature, but it's not the temperature. It really isn't. So what we have to do next, and I'm going to have to come over here since I messed up my own sheet here, my Q from A to B, B to C, C to A, and A, B, C, A. Well, we know that U is Q plus W. Well, Q then is going to be delta U minus W. So I've got the change in internal energy minus the work. Well, if I know the change in internal energy, I know the work. All I got to do is subtract. So we're going to take negative 13,507 minus 0, and my Q is equal to the work, because it was equal to 0. My heat is negative 13,507, and that is energy that left the system. I didn't do any work. I lost internal energy. Where did that energy go? Oh, it went to outside the system. It transferred it to the surroundings. That's what heat is. It's the transfer of energy from the system to the surroundings or to another object. So now let's look at BC. I've got delta U is 9,000 joules. Ah, crikey. And I've got the work is negative 6,000 joules. So Q is delta U minus W. So that's 9,100 or 9,017 minus negative 6,000 joules, or 15,017 joules. A lot of heat got transferred, and that's heat that's going into the system. That's from the surroundings into the system. It's absorbing energy. And from C to A, delta U is 4,490. The work is 15,000. Q is delta U minus the work. My work was, I'm just going to 4,490 minus, and this was a positive number, 15,000. And that's a negative number. So the heat transferred there is negative 10,510 joules. We gained. So we gained some energy. We lost. We're losing a lot. So let's take a look here. That's 0. So heat is delta U minus, well, that's going to be 0. And so the work is negative 9,000 joules, or sorry, it is negative 9,000 joules. And so the heat is negative 9,000. And that should make sense to us. If I were to take the heat from each leg of this and add them up, I will come up with negative 9,000 joules. So we are verifying that our cycle is working and it's true and that we've got this amount. So overall, I have lost energy to the surroundings. Work was done on the system, and the change of internal energy was 0 on the system. I know this is a really complicated problem, and what I hope I've done is shown you that this PV diagram looks super complicated, but if you really take heart, these 4 equations and these relationships and understanding how these are related to each other, the PV diagram is actually not bad at all. It's a nice clue. The one thing you're going to have to remember is that counterclockwise is positive work, clockwise is negative work. Easy peasy. All right. So our next topic of conversation will be specific heat and the energy absorbed by solid objects. And so not gases, although we could do gases with it. Just keep plugging, work on your assignments, and remember that we're all in this together.